Good morning, students. In the last session we have discussed about traveling wave tube. So traveling wave tube is an amplifier and it is an O-type tubes. It is an O-type tube. The O-type parallel field linear beam device. The TWT is a O-type tube, parallel field and linear beam device. It differs from the Klystron. So the RF field and the electron beam interact with each other over the entire length of the active region. So in the TWT, the RF field and the electron beam interact with each other over the entire length of the active region. But in the Klystron, the RF field and the electron beam interact with each other at the cavity gaps only. But here, the RF field and the electron beam interact with each other over the entire length of the active region. The main goal of this TWT is here, it slow down the RF wave. It slow down the RF wave which propagates at the speed of light. So it is the main goal of the traveling wave tube. Okay. So here the RF wave propagates at the speed of light, while the electron beams propagate at much slower velocities. The RF wave propagates at the speed of light and the electron beams propagate at much slower velocities. So to synchronize with such a beam, an RF wave must be slowed down to 1/13th of the normal velocity. Okay. And we have discussed about helix TWT. Here this helix TWT consists of an electron gun and a slow wave structure. So the electron beam is focused by a magnetic focusing field and guided through the center of the long axial helix. The slow wave structure is either the helical type or folded backlight. Here the signal to be amplified is applied to the end of the helix adjacent to the electron gun. The signal to be amplified is applied to the end of the helix adjacent to the electron gun. The applied signal propagates around the turns of the helix and produces an electric field. Here the applied signal propagates around the turns of the helix. See here the turns of the helix at the center. The applied signal propagates around the turns of the helix and produces an electric field at the center of the helix. So the amplified signal appears at the output. See here the amplified signal appears at the output. Here the helix is made positive with respect to cathode and collector. Here the beam is attracted to the collector and acquires a high velocity. So different forms of slow wave structures are commonly used in TWTs. So single helix, folded helix, and double helix, a ring bar, so like that. And these are the applications of TWT. Here the performance characteristics are: efficiency is 20%, output power is 10 kilowatts, power gain is 60 decibels, operating frequency 3 gigahertz, bandwidth is 0.8 gigahertz, and noise figure is 4 to 8 decibels. When it comes to applications, so the CW radar and radar jamming, so medium and high power satellite transponders output. So all these things we have discussed in the last session. So what is the need of slow wave structure? So slow wave structures are used to reduce the wave velocity in a certain direction so that the signal and the electron beam can interact, and for producing larger gain over a wide bandwidth. So this is the need of the slow wave structure. Here the four propagation constants are gamma 1, gamma 2, gamma 3, gamma 4. Gamma 1 is minus beta c root 3 by 2 plus j beta 1 plus c by 2. So gamma 2 is beta c root 3 by 2 plus j beta into 1 plus c by 2. gamma 3 is j beta 1 minus c, gamma 4 is minus j beta 1 minus c cube by 4. If you see the comparison between TWT and Klystron, so in TWT field travels along the beam, but in the Klystron field is stationary and only beam travels. So here in TWT the microcircuit is non-resonant. In Klystron it is a resonant type. The wave in TWT is a propagating wave. In Klystron wave is not propagating. In TWT the interaction of electron beam and RF field is continuous over the entire length of the circuit. In Klystron interaction of RF beam, electron beam and RF field, the interaction occurs only at the gaps of the cavities. So these are the differences between TWT and Klystron. And here we can see the important expressions in TWT. So phase constant, output power and gain constants, so gain parameter and frequency. Okay. Next, in this session we are going to discuss about M-type tubes. So M-type tubes, so magnetrons are M-type device are cross-field tubes. Magnetron are M-type device or cross-field tubes in which the DC magnetic field and DC electric field are perpendicular to each other. Here the DC magnetic field and the DC electric field are perpendicular to each other. So here the DC magnetic field plays a direct role in the RF interaction. In the M-type tubes, the DC magnetic field and the DC electric field are perpendicular to each other. So the crossed field magnetron is a microwave generator device that uses electrical and magnetic fields crossed at right angles to each other in an interaction space between cathode and anode. The magnetron principle is derived from the path of electron in crossed magnetic and electrical field. When an electron is injected into an electrical field, it will accelerate from the cathode to the anode in a straight line. When an electron is injected into an electrical field, it will accelerate from the cathode to the anode in a straight line. But if a perpendicular magnetic field is also present, then the electron moves in a curved cycloidal path by arranging the cathode and anode structure. Okay. See here. Here the electric field and the magnetic field are perpendicular to each other. See in this diagram, the electric field and the magnetic field are perpendicular to each other. So here when an electron is injected into an electrical field, it will accelerate from the cathode to the anode in a straight line. So if a perpendicular magnetic field is present, then the electron moves in a curved path. So here the electron moves in a curved path. So by arranging the cathode and anode structure. See here it is a coaxial magnetron. So this diagram shows a coaxial magnetron. So here it consists of a circular cathode inside a circular anode. So the coaxial magnetron, it consists of a circular cathode inside a circular anode. The electric field is, so here the negative side is connected to the cathode and the positive side is connected to the anode. The negative side is connected to the cathode. So in this diagram, in this coaxial magnetron, here the negative side is connected to the cathode and the positive side is connected to the anode. A magnetic field from an external permanent magnet has its lines of force perpendicular to the electric field. So here negative side is connected to the cathode and the positive side is connected to the anode. So assuming a constant magnetic field, so there is a critical voltage called Hull potential. So here the Hull potential is so it is EB square, capital B square by 8m 1 minus A square by B square whole square. Here A is cathode radius in meters, B is anode radius in meters, and E is electronic charge. This is 1.6 into 10 power minus 19 coulombs, and M is mass of an electron, and capital B is magnetic field density. Capital B is magnetic field density, and M is mass of an electron, E is electronic charge, B is anode radius in meters, and A is cathode radius in meters. It is the Hull potential in volts. So next, see the cylindrical magnetron. So what is cylindrical magnetron? So before this, the magnetron provide a microwave oscillation so of very high power. The magnetron was invented by Hull in 1921. Magnetron was invented by Hull in 1921. Magnetron is a self-contained microwave oscillator. Magnetron is a self-contained microwave oscillator. So it operates differently from linear wave tubes, so such as TWT and Klystron. So magnetrons are the cross-field tubes. Magnetron are the cross-field tubes in which the electric and magnetic fields are perpendicular to each other. So these tubes are known as M-type microwave tubes. Why it is called M-type microwave tubes? Here the electric and magnetic fields are perpendicular to each other. So if you see this is the cylindrical magnetron diagram. The cylindrical magnetron consists of a cylindrical cathode of finite length and radius A, at the center surrounded by a cylindrical anode of radius B. The cylindrical magnetron consists of a cylindrical cathode. See here, it is a cylindrical cathode. It consists of a cylindrical cathode of finite length and its radius is A. It is surrounded by a cylindrical anode and its radius is B. So here these cavities are connected between anode and cathode. So the cylindrical magnetron consists of a cylindrical cathode and cylindrical anode. Here the DC voltage V0 is applied between anode and cathode. See here, the DC voltage is applied between anode and cathode. The magnetic flux density is maintained in positive z direction by an electromagnet. So here this DC voltage is applied between anode and cathode. The magnetic flux density is maintained in positive z direction by an electromagnet. If the DC voltage and the magnetic flux are adjusted properly, under the combined forces, the electrons follow the cycloidal path between anode-cathode space. Here the open space between cathode and anode is called the interaction space. The open space between anode and cathode is called the interaction space. In this space, the electric and magnetic fields interact to each other. The magnetic field is provided by a strong permanent magnet. The magnetic field is provided by a strong permanent magnet, so mounted around the magnetron, so that the magnetic field is parallel with the axis of the cathode. So next, the types of magnetrons. Here we have different types of magnetrons. So negative resistance type. Next one is, second one is cyclotron frequency type. Third one is traveling wave or cavity type. So these are the types of magnetrons. So the negative resistance type magnetrons are useful at the frequency less than 500 MHz. The negative resistance type magnetrons are useful at the frequency less than 500 MHz. So these magnetrons uses the negative resistance between two anode segments. So the negative resistance magnetrons are capable of generating high power output, and the length of the tube plate is limited to few centimeters. So the negative resistance type magnetrons used at the frequency less than 500 MHz. So these magnetrons use the negative resistance between the two anode segments. So these are capable of generating high output power, and the length of the tube plate is limited to few centimeters. Second one is cyclotron frequency type. So these cyclotron frequency type are useful only for the frequencies greater than 100 MHz. Here the working of these magnetrons depends upon the synchronization between an alternating component of electric field and periodic oscillations of electrons in the direction parallel to the field. So third one is traveling wave or cavity type. So these magnetrons provides oscillations of very high peak power. So these are useful in radar applications. So the working of these magnetrons depends on the interaction of electrons with a rotating electromagnetic field of constant angular velocity. So these are the different types of magnetrons. So negative resistance type, cyclotron frequency type, and traveling wave or cavity type. So next, the characteristics of magnetrons are: efficiency is high, that is from 40 to 70%. Output power is 800 kilowatts, and the operating frequency is up to 10 gigahertz. The characteristics of magnetrons are: efficiency is from 40 to 70%. Output power is 800 kilowatts. Operating frequency is up to 10 gigahertz. And the applications are: in satellites and missiles, in satellite communication, in industrial heating, microwave ovens. So these are, and radars. So they are the applications of magnetrons. The important equations are the Hull cutoff potential, the Hartree potential, the phase velocity of RF wave in TWT slow wave structure, so they are the important equations of magnetrons and TWT. So see here, the problem is an X-band pulsed conventional magnetron has the following parameters. An X-band pulsed conventional magnetron has the following parameters. Anode voltage is 5.5 kilovolts, beam current is 4.5 amperes, operating frequency is 9 gigahertz, resonator conductance is 2 into 10 power minus 4 mhos, loaded conductance is 2.5 into 10 power minus 5, so vane capacitance 2.5 into 10 power minus 12, duty cycle is 0.002, power loss is 18.5 kilowatts. So here the compute the resonant frequency, the unloaded Q, the loaded Q, and the electronic efficiency. So they are the given values. So V0 is 5.5 kilovolts and I0 is beam current 4.5 amperes and the frequency is 9 gigahertz and GR is 2 into 10 power minus 4 and GL is 2.5 into 10 power minus 5, that is resonator conductance and loaded conductance, and vane capacitance C is 2.5 picofarads and duty cycle is 0.002 and power loss is 18.5 kilowatts. Here the resonant frequency is, here we need to calculate the resonant frequency, the loaded Q, unloaded Q, and the electronic efficiency. The resonant frequency is omega r equal to 2 pi f, so substitute frequency here. And the second one is the electronic efficiency. It is the electronic efficiency. So V0 I0 minus power loss by PDC. So substitute V0 I0 and power loss and PDC values, then we get 25%. So next one is, so a normal circular magnetron has the following parameters. The inner radius is 0.5, 0.15, and outer radius is 0.45, magnetic flux density is 1.2 milliweber. So determine Hull cutoff voltage. Second one is determine the Hull cutoff magnetic flux density if the beam voltage is 6000 volts. Here A is 0.15 meters, B is 0.45 meters, and B0 is 1.2 milliweber per meter square. The Hull cutoff voltage, so see here and substitute all these values, then we get Hull cutoff potential is 5 kilovolts. And second one is Hull cutoff magnetic flux density is, so B0 equal to 8 V0 m by c whole power 1 by 2 by b into 1 minus a square by b square. Here we get it is 10.43 milliwebers. So in this problem, In the magnetron, find the Hartree potential if the magnetron has 8 resonators, each tuned to 2.95 GHz with cathode radius of 2.5 mm and an anode radius of 5 mm. So here the magnetic field is 0.27, the frequency is 2.95 into 10 power 9 Hz, and number of resonators is, say, n equal to 8, and A equal to 5 mm and B equal to 2.5 mm. So we know that the Hartree potential, it is 2 pi Fb by n into B square minus A square. Here F is 2.95 into 10 power 9 and B is 0.27 and small b is 2.5 mm and A is 5 mm. So substitute all these values, then we get Hartree potential is 11.7 kilovolts. Okay, thank you.